Hi, everyone. We're excited to have you here today. So we have an exciting meetup. Today, we're going to be talking about validating jet engine data using machine learning in Cloudera machine learning. Something very near and dear to my heart because I used to work with jet engine data in the past. And so did our guest speaker today, Nicholas Pelez. We actually worked together in the past. We've also got Tui, George, and Bill helping out with your questions, either coming in from YouTube or LinkedIn. Now, something before we move on, we're going to have two QA sections. We're going to have a first one where you can ask questions about the slides that you're seeing, just so that we can get your initial questions out of the way. And then after that, we can move on to the demo. And after the demo is done, we'll have another QA session so you can ask your technical questions. Now, some of you are here for this next piece, the prizes. Now, we have two winners today. The first winner is going to receive what you see on the left there. So a great t-shirt. Everyone's looking for that t-shirt all the time. Duffel bag. We always love hoodies, right? And I'll say the Cloudera hoodies are pretty comfortable. And then we also have the second set of prizes there. The metallic logo tee, a white t-shirt with the Cloudera logo. I actually wore that yesterday. It's also very comfortable. And that clip speaker. So now, I think it's time that we invite the guest speaker in. Nick, are you there? Hey. Oh, you're on mute.
Aha.
There, now I can hear you. How's it going?
Pretty well. Thanks for the introduction. So,
Yeah, of course.
as Mark said, we actually worked for several years in the past. Our previous job, we did a lot of the data manipulation, the trending, and the analysis on both military and commercial jet engines. So we worked with a lot of different engines, a lot of different kinds of data. Learned a lot. Fun job, right? And so we kind of have a passion outside from work for aircraft and jet engines in general. So we welcome all questions as we go through this, presentation.
Yeah,
So
we love answering those. And what you have here today is actually some of the same way we used to like justify the way we save money for actual airlines, right? Like the same kind of way you built that model today is what we did in the real world.
Right. And we'll go through kind of what we're going to do, the reasoning why we're going to do it, and why it's important. And we kind of come from a background where we've seen it happen in real life, and we've been the reason that flights were diverted back. So it should be an interesting little session here. All right. So I need to mute one of my cameras. There we go. Can everyone hear me? Can you guys hear me all right? Cool. All right. So we're going to start off with some background, the scenario we're going to talk about today. Like Mark said, we're going to be talking about how to validate a jet engine analysis kind of system. And you'll see why I say a system. It's not a one specific thing. Using kind of a cloud-based ecosystem, right? So we're going to be using the Cloudera data platform, which I'll kind of cover more into why we're going to use that. But first, the motivation, right? So I'm sure a lot of you here have flown on a commercial airline, right? If you're going more than a couple hundred miles from home, there's a good chance that you've been on one of these planes that have, two or more of these engines, right? These commercial airliners fly these engines 3 or 4 times a day, 7 days a week, right? They operate on very thin margins, so they need to run these things as much as they can while being very, very safe about it, right? There's a reason that flying is actually the safest form of transportation, right? It's a lot more dangerous to get in a car. Not a lot of people realize that, but it's true. There's about 45,000 flights daily, right? And over 10 million passengers a year fly on commercial airlines. So it's very important to them to keep their business afloat, to make sure that these engines are running optimally always, right? And that they get maintained on a proper schedule and that they never have any kind of mishaps, right? So we're going to be looking into how they do that, right? And how essentially they build a modeling process that tells them when to do maintenance on these engines. So the data we're going to be using today is actually a synthetic data set made by NASA that covers 4 different flight scenarios and gives you mock data with a fleet of 100 or so engines, right? With a whole suite of sensors, right? And a whole lot of flights for each engine. They give you a training set where they tell you exactly how much remaining flights an engine has before it fails, right? And then they give you a test set where they only give you the sensor data and a fleet of 100 engines, and they challenge you to say, okay, come up with some kind of modeling system that tells us when or how many flights these engines have on the last point of their data, right? And then they give you a separate data set that gives you the actual values so that you can compare how well your model kind of performed, right? So our first goal, right, and we're going to kind of do this in two pieces, right? The original data set, the challenge is to figure out how much useful life remaining or how many flights are left on a particular engine, right? But we're going to take it a couple steps further. We're not only going to say how much useful life was remaining on this engine, but we're going to actually build a classification model to say, we're going to set a threshold and say aircraft or airlines would like to know within 40 flights if they need to maintain an engine, right? This is important because it lets them logistically plan, right? So a lot of airlines have, say, home bases, right, where they have a lot of their maintenance facilities. So if they can plan maintenance ahead of time, right, they can actually have the parts or the spare engines ready and waiting, and they can, have less delays. They don't have to cancel flights, right? It can save them a lot of money to be prepared logistically for this engine maintenance. So we're going to build a classifier that after we predict how many flights are remaining, tells us whether or not this engine at the end of its flight needs maintenance or does not need maintenance within that 40-day threshold. Then on top of that, in order to kind of tie it all together and bring it into an economic point of view, we're going to assign values to the outcomes of this classifier, right? So that way we can figure out how much potential money would be saved, whether or not our classification correctly classified an overhaul was needed or not. So let's go into a little bit of what the data looks like, right? The data set is going to have a number of flights from a fleet of 100 engines. I say a number of flights because they're actually different, right? So engine 1 may have 160 flights. Engine 2 may have 80 flights. Engine 3 may have 300 flights. I think they did this on purpose because in the real world, you don't fly every engine exactly the same amount of time or the same places, right? So they put that kind of mix into the data. For each engine, for each flight, you have 24 sensor readings, right, from different parts of the engine. This is important because these engines are very well instrumented. And by that, I mean there's sensors all over the place, right? It's not kind of like your car where a check engine light goes on, you take it to the mechanic, they scan it, oh, it's this. No, you are monitoring these things in all sorts of different ways, right? So they provide 24 different sensor readouts. The test data only contains the sensor reading. The training sets contain the sensor reading and the useful life remaining. That allows us to easily train our models, right? So the first thing we're going to do is we're going to go through those sensors and we're going to draw correlations to see if these sensors correlate with how much remaining life this engine may have, right? So if you look on the left, that setting one sensor that we have, right, it doesn't look like it correlates very well to the remaining useful life. It's just a shotgun plot, right? It's all over the place. You can't draw a line through that and have any kind of fit. But on the right-hand side, right, there is some correlation there. You see it tails off. That sensor is T5, right? It's a temperature probe near the end of the engine. And you see that as that temperature goes up, right, the remaining useful life goes down. So there's a correlation that can be drawn there. So what we're going to do is we're going to take all the sensors that have some kind of correlation, and we are going to train a model on them, right? This model, we're going to be using XGBoost. It's just an open source model that performs very well, right? It's going to predict how many remaining flights a specific engine has, right? And we're going to train it based on the training set. Then The classifier is going to, at the start, we're going to set a threshold of 40, and then we're going to have the classifier say, if it was less than 40, then that engine needed an overhaul, less than 40 flights remaining, right? And if you think about it, right, that's about a week or so of flying for one of these engines, right? That's not very much. That's enough to give the airlines a heads up, but not too much that they're going to sit on their hands and not do anything for a little bit, right? So if it's less than 40, we're predicting that that engine needs an overhaul. If it's greater than 40, we're saying that that engine is okay to keep flying, right? Then, based on those outcomes, we're going to assign a dollar value, right? So on the top left, we have what we consider to be a timely overhaul, right? A timely overhaul means the classifier predicted that the engine needs an overhaul, and it was right. The engine did need an overhaul. So we're saying an airline is going to save $500,000 because they can logistically plan to have that engine ready, to have a spare engine ready to go. They have no downtime on that aircraft, right? They could pull it in the hangar, change the engine out in a couple hours overnight, roll the engine out, and it's good to go for your 7 a.m. flight, right? So that is the best case scenario, right? Then on the top right, this is where the classifier determined that you needed an overhaul, but you didn't. You actually had a little bit of flights left, right? We're saying that the airline loses $150,000 worth of potential revenue because you could have flown that engine safely a couple more times, right? And that, with some thin margins, that could, lose you some money if you pull an engine too early. On the bottom left, you have the worst case scenario, which is that the classifier said, you are good to keep flying. Your engine is fine. And it was not, right? Now, this could lead to extra engine damage, right? You could have worn the parts past where they're supposed to wear, and that changes it from a refurbishment to a replacement of certain parts. To anything worse, right? Like having an actual engine failure, having the engine have to turn around, the aircraft turn around and come back home. And you may lose, a lot of money by trashing one of your engines, right? And just to sway any people that are a little worried about that scenario, not very known fact, any commercial airline that you fly on is designed in such a way that you are never using more than 40% power on any engine. What that means is that if you lose one of your engines on takeoff with full passengers and full cargo on a hot day, and you lose one of your engines, that other engine is perfectly capable of cranking back up to 100% power and getting you up off the ground, turning you back around, and landing you safely, right? So if, the worst case scenario, if you lose an engine, you're still okay. They are designed to be safe in that sense, which I always thought was very interesting. So we're saying if you miss an overhaul, if our classifier says that you were good to fly and you weren't, we're going to assign a loss of $1 million because that's a very bad scenario for us. And then on the bottom right, we're saying the classifier said that your engine was good to keep flying, and it was right. The engine was good to keep flying. Nothing changes. We take no action, so there's no cost benefit there. So that's kind of the groundwork, and that is how we're going to validate our predictive model, right? We're going to actually assign the cost value and see for this fleet of 100 engines how it all would have stacked up. So how are we going to do this, right? What's the environment we're going to do this processing in? In this case, we're going to use Cloudera machine learning, right? So what is Cloudera machine learning, right? Well, it's been described as a self-service data science and data engineering in a single portable service as part of an enterprise data cloud, right? It's a lot of words, but in a more simplistic sense, it lets you do data science, it lets you do machine learning, it lets you run code in an environment that you can share with other people that you might be working with and all kind of share the same resources, the same libraries. You can look at each other's sessions. You can code in the same place, right? That's really important if you're not, in a little silo working on your own, which is very, very rarely the case, right? So I'll tell you, it is very nice to be able to just spool up and open a project that you share with somebody else. All the libraries that you two have been working with, or 3 or 4 or 5 or 10, are all already there. They're already installed. You can share code back and forth. I know Mark and I actually have used the same workspace before live on a call, just debugging the same code until one of us figured it out. like, oh yeah, just look at the console. There it is. He's like, oh sweet, grab it, throw it in the code. It's a very good development environment. And it also has extra things built into it, right? So machine learning specifically, you can actually, once you've got a model saved, you can deploy the model within machine learning, and it'll open up an API that you can hit from outside, and you can actually send inputs into your model and get, a result. And that lets you go from creating a model to serving it up really, really fast. I mean, like 10 minutes, right? That's really good if you have, say, a third-party application that you're going to be using your model in, right? You can link to machine learning really easy, develop a machine learning, deploy your model, and it's there, right? You can interact with a third-party app easy. Speaking of third-party applications, you can even host your application within machine learning itself, right? So we'll actually demo that a little bit at the end here. As Mark mentioned, we have a Raffle. We are going to be using machine learning, the little third-party application that Mark himself created in CML, the Cloudera machine learning, to do the Raffle. So hopefully that'll be kind of interesting. So there's one more thing that machine learning has that we're going to be showing at the end as well, which is called experiments, right? What experiments let you do is it lets you pick certain metrics that you're curious about, right? In our case, we're going to be showing the amount of money saved, right, for a specific scenario. We're going to be showing the model's performance using the area under the curve, right? And we're going to be showing the classifier's performance, right, with showing the classifier accuracy. What it lets you do is embed these metrics into your code and giving it different input arguments, right? You can run your same set of code, numerous times and have a nice, concise place to look at just the results, right? And then if you're interested in the results, you can then dive in to see what the actual session looked like, what the code looked like, what the outputs were, and so on and so on. And we'll show that at the end. This is how we're actually going to, because at the beginning I said that there are 4 different scenarios, right? So we're going to actually take each one of those scenarios for different, airlines that may have different thresholds of flights, and we are going to show how our model would have performed under each of these circumstances. So Cloudera machine learning lives in a bigger ecosystem, which is what we call the Cloudera data platform, right? In this case, what we're doing is on the public cloud, but it is really a hybrid multi-cloud. And, what does that mean? It means that it operates both completely in the cloud or on, a private installation somewhere on premises or somewhere in between, right? That's the hybrid part of it, right? You can do certain things on the cloud. You can do certain things locally. It just depends on what makes the most sense for you specifically, right? It also is multifunction. It does a whole bunch of different things, right? We're specifically going over machine learning, but I mean, it does everything from data engineering, ingesting. It does data warehousing for you, right? It does all sorts of different things. You can bring in streaming data. You can do streaming analysis, right? There's a ton that it's capable of. And then on top of that, it has common security and governance, meaning that you can do all of your permissions, all of your, you can follow where all your data came from, where it all ended up, all in kind of one center place. And if you're the one that has to manage these systems, that is, hugely important, right? So before we go into the demo, we want to hit the first Q&A. I know I've kind of talked a lot. I've had a decent bit of coffee, so I apologize if I'm speaking a little fast. But let us know if you've got any questions before we jump into the actual demo.
Hey everyone, looks like I'm back. Yeah, and just want to say again, I didn't emphasize this as much at the beginning, but those prizes, they will be at the end. So make sure you stick around through the first QA, which is right now, and the second QA. I was here making notes while you were talking, Nick. One thing I want to also put a note on is those cost values, right? I know we said we base it on something we did in the past. Those are accurate to like the actual engines because it changes depending on engine type, on service plan. So many factors go into it. So those were just some nice round numbers, which were kind of close, so that you could see how changing your model parameters can impact when the costs and depending on how soon you're pulling off engines and stuff like that. Also, speaking of streaming, right? It's a fun thing. We should try getting your Corvette to stream in data show. We did something. You did something like that already, but that might be a fun one as well. I'm just checking the questions here.
Yeah, we do want to do that in the future. So like we said, it does bring in streaming data. There's a really interesting thing called Minify, which is NiFi is like a flow control platform, I guess we'll call it. And Minify can live on like something as small as like a Raspberry Pi, right? And so at some point we want to hook that up to my car and live stream sensor data to the cloud to do stream analysis on it, right? I have a very heavily modified car that I'm constantly breaking, and because of that, I need to be looking at the data from it all the time and tweaking the actual, tune the car's engine operating parameters like constantly, which would be really nice if it just always streamed into the cloud and I can pull them whenever I want. I think we lost Mark there. All right.
Hey, everyone. Okay, I'm back. So we do have one question coming in right now. It's a user asking, in CML, can you import a model that's already trained into CML and then use it? I know of one way just because I've done it with Python. So what I do is I wrap up my model as a pickle object, and then I load that pickle object once it's in there. So that's something I do for deploying models as well. That's something CML can do. So what I do is I train my model, I save it as a pickle object, and then when I'm deploying that model, I load in the pickle object so that it's quick and easy. You don't want to like train and then answer whatever request is coming in through that way. We have some good resources that show models in that way that we could probably point folks to, because that's the quick answer, right? There's a whole background there where you can actually make API requests in CML to a deployed model. So yes, there is a way. It's the short answer.
Yeah. Although I would almost make the argument that if you're creating the model outside of CML, you could also just do it. You could take your same, say, Python code that you're using to make your model, and you can just run it in CML, save it to the local file, and it's already there, right? So that way you can do the tweaking in there too.
All right, on that note, I think we're ready to go into your actual demo, the moment that everyone's been waiting for. So I will see you once you're done.
All right. Give me 1 second to switch this here. Hopefully everyone can hear me all right. Okay. So, that's not what I meant to click. So when you open up CDP Public Cloud, right, this is kind of the home page here. This is what we call our experiences. These are at a high level, the different things you can do with your data, right? What we call the data lifecycle. So there's data engineering that lets you, bring in a whole bunch of data. It lets you run jobs, right? In our case, I've used that mostly with PySpark, where I'll run a whole bunch of jobs to bring in data from, say, S3 and do some kind of transformation on it, right? Maybe enrich it some, link it with other data sources, and dunk it into like our data warehouse, either Hive or Impala. So that kind of segues into data warehouse, right? That's where we would store our data, and it actually has some pretty neat visualization and like interactive GUIs, so you can go run SQL queries against it and things like that. Operational database lets you serve that data up, right? Lets you interact with it from outside through something like Phoenix or something like that, JDBC. And then machine learning is what we are going to go into, right? So machine learning is what we've been talking about. It's what we call Cloudera machine learning, or CML. Within CML, you have different workspaces, right? So I've created one called NASA Engine Analysis. A workspace is where you can collaborate with a whole bunch of people, right? And kind of compartmentalize what you want to show certain people or work with certain people. Within a workspace, you have projects, which gives you kind of more fine-grained control, right? So I can have specific projects that I share with only Mark, right? Because we're doing something that's kind of ridiculous. We want people to laugh at us, right? Or I can have workspaces that I can share with a whole bunch of people, right? Where we're doing something that's a little bit more production sided and, we need a lot of people's input, right? In this case, this one's just me. So if we go into the project, right, we've got all the files, right? And here are the testing sets, the training sets. These RULs are the NASA provided correct answers for the test sets. They put them separate. I'm not sure if they were trying to save us effort or not. It kind of ends up being more effort, but either way, that's what those are. Then we've got the jet engine modeling Python file, which is actually going to create our model. We're going to actually dive into that. And the utils Python file, which just kind of has the backend functions to our modeling file to make it clean. You have a CDSW build file, which lets you automatically install certain libraries that you might know you want to use. And so let's just jump into it. So this lets you look at the actual file itself, right? That's kind of cool, but we're not going to look at it here because there's a better way to do it. So we can open this file in the workbench. What the workbench is essentially, it's an interactive IDE, right? So we're going to start a new session, right? We're going to run Python 3. We can tell it how many resources we want, right? What we're running right here is not very heavy. We're fine with the default. We don't need any GPUs, so we're just going to go ahead and start the session. While that loads up, let's take a look at the code. Hopefully you guys can see this okay. So, there's some imports. These are the libraries we're going to use. These are the input arguments. They're going to be important later on because we are actually going to be tweaking these in the experiment section of this. But what these dictate is FD001 stands for the scenario. There's 4 different scenarios, 1, 2, 3, and 4. The cycle alert threshold is how many flights the airline would like to know ahead of time when the engine would need an overhaul. So we're starting with a default of 40, but we're going to be tweaking that in the experiments as well. So if we scroll down, right, the first thing we're going to be doing is we're going to be filtering out our training data, right? Like we said, we want to only use the parameters that correlate, right? So we're going to be making all the correlation plots, and we're going to be taking the ones, we're going to be removing the ones that don't correlate, right? If you've done a lot of machine learning, you know that a ton of the effort involved is in cleaning your data up, right? And getting the most representative data for what you're trying to model out of what you actually get. Having lived, in this jet engine analysis world for a while, I can tell you that there is a lot of garbage data that comes out, right? There is a lot of cleaning that you have to do, right? I have never, been in some miracle world where I get a data set and it's like, beautiful. This is all exactly what I need, right? It's so far never happened to me. So this is going to do all that cleaning and that correlation. Then we're going to be creating the model using that now cleaned data, right? We're using XGBoost. Here are the parameters that we're putting into this model, right? It is a boosting algorithm, so the number of estimators we tweaked a little bit. And again, there's probably room for improvement here. I will say that in a real world scenario, right, a fleet of 100 engines and 100 flights or so for them is actually a relatively small data set, right? We worked with a lot more data in the past, right? These engines, like we said, they fly 4 times a day, 7 days a week, right? So 150 flights is a relatively short amount of time, right? That's maybe like a month's worth of data. So in a real world, this model might even perform a lot better because you would have an order of magnitude, more data to train it on. So then once we have our model created, right, we are going to be pulling in our test data, and we're going to be running our model on our test data in order to estimate how many flights remaining each one of these engines has at the end. And then we're going to do some calculations, right? These calculations include training the classifier and classifying. We've got, again, the dollar amount associated to each classification outcome, right? And at the very end, right, these are applying the dollar amounts based on the classification outcome. And then this is a very important part here. these are the three metrics that we are tracking, right? So you'll see CDSW stands for Cloudera Data Science Workbench. That's the library that lets us output these metrics to our experiment side, and it lets us look at all of our results in one place, right? And then we're just going to print them so we can see them, right? So with this all said and done, we're going to hit the run button, and you'll see on the right hand side here, right? This is going to be my interactive session. I'm just going to move this over here. So if I run this file, right, it's going to start running our machine learning code, right? We're doing our correlations now, right? When it's done with those, it's going to train the model, right? Once the model's trained, it's going to make the classifier, and then we're going to get our classification results. Now, remember, this is for one specific scenario. This is for scenario 1 with a threshold flight of 40, right? And now we can see with the results there that our classifier hit a 93% accuracy, which resulted in $4.85 million of savings in this specific scenario. Our area under the curve was 0.89, which is pretty solid, right? So now that you've kind of like, all right, it seems to work for the scenario. How will it work for the other ones, right? How will it work if we change the thresholds? Well, that is when we go back to our project. Now we can use the experiments tab, right? So there's some spoilers there. Let's not look there. So to run a new experiment, right, all we do is we tell it the code that we'd like to run. In this case, right, jet engine modeling.py. So we're going to run. We're going to give it the input arguments. So we did scenario 1 at a threshold of 40, right? In this case, let's do scenario 2 with threshold of 40, right? We're going to run Python 3. Again, for each experiment, we can set an engine profile. In this case, it's, again, not very heavy lift. We're going to leave it to the default. And then we can put a note here, right? We're going to say run 2 threshold 40 flights. And we can start the run. Now, I've saved us a little bit of time, and I've run all of the scenarios for 2 different flight thresholds, right? These actually run really quickly, but I figured that it is not very exciting to watch me type this all in, so I did it beforehand. And here you can see all of the results in one place, right? And you can see that area under the curve, accuracy, and savings are the metrics that we output from within our machine learning code. And now we can look at them and sort by them here, right? So we can look and say, okay, well, the original one we ran, right, gave us a 93% accuracy and a savings of 4.85 million, right? At a threshold of 50 flights, it looks like it, did a little worse, 2.5 million in savings, or 88%. The takeaway here, though, is that you can use this to tweak your models, or you can use them to see what scenarios your model would actually perform better in, right? And that gives you not only confidence that it works across a lot of different things, but it also serves as a good way to tweak and tune to see where you could improve your model, right? So if I were to have to deploy this, in a real scenario, I would look and say, wow, for scenario number 2 at 40 flights, right, we saved almost $14 million. What worked so well there that may not have worked so well for this one scenario at 50 threshold, right, at a threshold of 50 flights. And the cool part about this is that all of the experiment code that ran is accessible, right? So I can click into this run and I can go to the session and I can actually go and look through, what happened in the code, right? What were my correlations, right? What were all my outputs? And then I can use that to go back and tweak and refine and improve my model, right? So by the end of the day, when I have a good, a model that I'm happy with, I can also go back and show across the board, this is how well it all performed. Then when you're done and you have that, nice fancy model, right, you can go ahead and you can deploy it, and you can use some kind of third-party app, right? And you can pass it off and say, here you go. Now when we update the model on our end, right, you are automatically tied into it. And it kind of helps the whole development lifecycle. So that kind of wraps up the demo. So I kind of went through a little fast, but let's go back to a Q&A.
Hey everyone, I'm back again. All right, I think before we get to this second set of Q&A, we're going to talk about some of the resources that we have for you. So if we could put that up on the screen. Now, Nick and I are part of the user marketing team, and
we lost Mark there. Sorry. Give us just 1 sec.
hey, all right. So that Cloudera users page is going to link to a lot of different content, videos, tutorials that the user marketing team that Nick and I are on creates. That's where you can see some of the other cool stuff that Nick creates. And also George, who's on this call, looking at the questions, creates those great tutorials. So there's also the CDP video tour. That's a really nice way to get an intro into all the different stages of the data lifecycle that CDP can support. We also have the Future of Data Meetup page. That's probably where you heard about this, unless you saw it in your LinkedIn stream or got an alert, or if you saw it on YouTube. And then we also have the Cloudera Now virtual event. That's an event that already happened, but it's kind of our big announcement time. We go over some of the technical stuff that CDP brings to the table. Nick, I don't know if you want to add anything to that.
Yeah, so I will say that there is actually a video on there that shows a deployment of a model in CML and interacting with a third-party application. So if you are curious to see the kind of full scope of it, there's a bunch of stuff on there that you might want to check out. And if you want to do it yourself too, like you said, George, who's also on this call, he makes tutorials, right, that include all of the assets. So it's very nice to be able to actually walk through it yourself.
Yeah, I guess a quick example of that is something I like to do is I build these little React sites, which I'm not good at all at. So they look very bad, but I'll make the React sites make requests to my models in CML. So that way I can just build a nice little front end, and then I host the model in CML, and then I can give it some parameters. Like I did one with house, predicting the prices of houses. And I put in some of the how many bedrooms, bathrooms, submitted that to the model in CML. It spit an answer back out at me. My model wasn't trained great, but it worked. So Nick knows that.
Well, turns out it's pretty hard to predict house prices.
Yeah, you got to do a lot of extra work that I don't know about. I'd rather stick to the jet engine stuff. I understand that more.
Agreed.
All right. So I think now it's time for the second part of our QA. Before I get to the questions, a couple things I want to mention here. So if you did join through Meetup, you will be getting a follow-up survey. If you could fill that out, we'd love your feedback. We want to make this better for all of you, right? We have fun doing this. We want this to be fun for you as well. Additionally, we'll give you a link after this is all done, whether it's on LinkedIn or YouTube, where we're going to answer some of the questions that we don't know the answers to, because we know some stuff, but not everything. But any questions we don't get to, we'll try to answer in that follow-up link, whether it's going to be a community post or a blog post. Right. So let me move over to the question tab here.
I'm going to ruin the Q&A screen for 1 second. Apologize. I just want to move this off that screen. There we go.
All right. Now, we do have one question here, which I thought you'd find interesting, Nick. What is the data volume for this use case? And they were hoping it was going to be a large data volume. I think people would be surprised to learn that once you're in production, at least with jet engine data, the data volume's not huge anymore. It's mainly when you're doing development flight tests where you have a lot of data.
Yeah, actually, that's a great question. So when it comes down to it, right, these engines are pumping out a ton of data, right? So depending on the type of data. So say if you're looking at a commercial engine and you're looking at something like vibrations, right? Which is definitely something that is very, looked at with a lot of scrutiny. You may have a sensor that's pumping out something at,
Oh,
this here.
okay. You're back, Nick. I can hear you. We left at 2000 hertz.
Yeah. So you may have, vibration sensor data that pumps something out like 2000 hertz, and the data implications there are pretty huge. But when it comes down to actually analyzing the data, right? Unless you are specifically the vibration guy that is super, interested in how this specific flight condition interacts with your specific part of the engine, you're not going to be looking at all that data, and you don't need all that data. So what you do is you have an intermediate step, right? Where you say, okay, give me that, gigabyte worth of vibration data that we got off that flight and boil it down. Give me the maxes, right? Let me see what the maximum displacement was, where the worst vibrations were, and throw out everything else because they don't matter, right? And why that's important is because, like we talked about earlier, as far as training a machine learning model, right? A big part of it is curating your data to give you answers that actually matter. And that is a huge push, right, in the jet engine world. So on the military side, I've worked on 3 different generations of engines, right? From engines developed in the 70s to engines developed, in the 2000s. When it comes down to it, right, the actual data you end up with at the end of the day is very similar because what you end up doing is you end up getting rid of 95% of the data that comes in from these newer engines, whereas the engines that may have been designed in the 70s were off the bat only giving you the important stuff, right? So while there are some development benefits to having so much data, when it comes to the day-to-day operations of it, more data is not always better.
Right. Sorry, I'm just reading the questions here, queuing up the next one. But yeah, you'd be surprised how much pre-processing happens even on the plane before it gets sent to us. So like I said, development flight tests, you get a lot. But this NASA data set, how big was it?
It was about 100 engines and 200 or so flights per engine for each set. So, I don't know, maybe
like a gig or a few.
Yeah, maybe a million or so flights.
Right. Okay, so let's move on to
thousands of flights, but
yeah, we can go on forever about this, but I want to make sure we get to some of the questions. So here's another one. Now, does CML decide which algorithm you use to train and test the models, or does it let you use any kind of your choice? And the answer there is CML was designed to make sure that the data scientist has pretty much all the control. You decide what model, what the parameters are. It's not one of those machine learning platforms where it like does the machine learning portion for you. It lets you write the Python code, the arc, and no, use PySpark, right? Yes, you can write Python, R, Spark. Basically, you write the code and it'll do it for you. It just has some nice features like experiments, models, even applications that make that easier for you. So,
right,
Nick, I don't know if you want to add on anything.
No, I mean, just when I was developing this, right, like I went through a few different models myself, and I couldn't imagine giving that freedom up to any kind of software. I'd like to have control of the model that I use.
Right. Okay, so here's another question. So how do we integrate this machine learning development environment with our data when we have that data managed and hosted in the public cloud? So this is where the whole CDP platform kind of comes in, because you have, as Nick was saying before, applications or tools to help manage every stage of the data lifecycle, right? From ingest through to machine learning, data warehousing. So you can import that data into the platform, right? Whether it's Hive, Impala, then you can access that data in CML. Now, if you're just using CML, you could also upload that data directly into CML. But if you're working on larger data sets, then that's where you would have that data stored in HBase or Hive or Impala. or Nick. I don't know if there's. I think
Yeah,
those
I
are
mean,
pretty much the ones.
yeah, that is. But it's a good point, right? So like you having the data warehousing solution that's tied in to CML, right? Like lets you link your data up to a huge data set if you need, and then you can kind of split the pre-processing from the machine learning and serving aspect of it, right? So you could have, a team of people that live in your data warehousing side that are constantly running jobs that clean that data up and push it into, more curated tables that are kind of the summary of the important things that you need to know, right? Such as things like alerts or specific averaged flight data rather than an entire flight, right? And then you can have a team in CML running models against just the curated code, right? And since you can link straight to that data warehousing, both of those teams can be running in tandem, and they'll always have the most updated information without having to kind of manually push or pull from anywhere.
Right. And sorry. Yeah, and it's all cloud native, right? The way that CDB works is going to work with the object storage that cloud uses, or so basically the security and lineage, right, can be tracked all the way through. And sorry, I forgot the point I was going to make. Sorry, moving on to the next question. Is there a key point that you have to consider when cleaning up the data with a huge amount of volume? And I'll let you start with that.
Yeah, absolutely. Right. So you have to figure out, right, what the minimum amount of data that's useful to you is, right? But also, and this is something I've kind of learned from experience, it has to be kind of done in such a way that if you decide later on that you did need something else, you can still retrieve it, right? So, for example, this is kind of a real world scenario where we were throwing out a ton of vibration data, right? Because they told us that, X company said that they are no longer looking at this, right? And that development part of the cycle is done, right? And then it doesn't matter anymore. And that was hundreds of gigs of data. So we cleared it from we used a relational database back then, right? And we cleared it all, right? And there was processing, right, that was done to this data before it was loaded, right?
Oh yeah, sorry. Let me interject. To be clear, we didn't delete the raw data. The raw data was all still there. This was the processed after
right.
data. We stored that in the RDS.
Right.
Or not RDS, but in the relational database.
We took, from terabytes of this vibration data, we, took out these specific parameters. We did some averaging, we did some time windowing, and we loaded this data to our, relational database. We had this monstrous table, and they told us, yeah, we don't need that anymore. You can get rid of it. Okay, cool. So we did. Well, a couple months later, there was a specific problem that they were looking for, and they said, hey, is there any way that we can pull these specific parameters back? To which everyone just kind of went, maybe.
How many weeks?
Yeah. When do you need this by? Oh, well, preferably in the next 2 weeks. And the answer was, no, we can't do that, right? And that was not only a limitation of how we set up our data processing, but also kind of the limited resources we had, right? Because this was all, a server that was on premises, right? We didn't have the ability to just spool up a ton of resources for a short amount of time, like you could do on something like public cloud, right? Where it's
to be clear, we also weren't using Cloudera. It was all like our own custom built code.
Yeah, this was all even homegrown. Yeah. This was some homebrew code,
as they like to call it.
Yeah. Whereas if you had something like this, public cloud and this ability to just expand your resources almost limitlessly, right? Then our answer could have probably been, you know what? Yeah, we can get this for you in a couple of days, but it's going to cost you this amount for the compute resources that we're going to need to spool up. But not having those compute resources, right, We can't call up Dell and be like, hey, we need 7 more rack servers and we only need them for another week. Can you just like come install them and then take them back when you're done? Right.
Yeah. I think something also to consider is when you're cleaning up the data, always expect it to change. So that's something that I learned very quickly at the beginning. I looked at the initial set of data, I set up the process to bring it in, and I didn't expect that over time things would change. So I didn't have anything set up to really alert me like, oh, these have now skewed. So like I would hard code some kind of like some industry facts in there, let's call it that. Uh, and then suddenly things would change. And so you want to, in your cleanup process, right? So we would do this in like NiFi, for example. That's what we have to kind of stream data in, or in Spark Jobs. You want to set up some alerts for yourself to make sure that if the data does change from what you're expecting, that you catch that, you get alerted so that you can fix it. And then set up your process in a way that makes it easy to reprocess that data again. Like I would kind of, if data couldn't get processed, put it in a queue, right? And then once I was able to fix it again, I would be able to run that data back through the queue. So that's kind of a trick that I learned very quickly while I was figuring out how to do that.
Yeah, fun example of data changing underneath your feet, right? We got a call from an airline one time saying, hey, what are you guys doing? We haven't gotten data for all of these engines in the past 2 months. So, we're, oh God, what did we mess up? What did we break? And we go digging into the source data, and it turns out that they were feeding us the engine serial numbers backwards now. They didn't tell us anything. It was just, they just decided that they were going to start reading them in reverse. And our code not only wasn't prepared for that, but it also didn't alert us that it wasn't processing these. It just happily dropped them on the floor as an engine serial number that didn't make sense. Right. So, once we were able to get it remedied, it was fine, but it's the kind of thing that went quiet for 2 months. Right. Whereas you kind of can set up some alerts to let you know that you're not just leaving data on the floor.
Right. There's a quick question here. Someone wants to see the React pages that I created. I think you can see some of them in the video that Nick made. I think you changed it, right? It was house predictions, and then you changed it to do you change it to engine models after?
I think I did 2, but we're gonna show a React application for the Raffle here. So if you stick around,
I really hope it works today. Warning to everyone, I made it in about a day, and like I said, I'm not the best web developer. I did C# before, so hopefully it works. Test it live. Okay. All right, just waiting for a couple more questions in here before we move on. I'm thinking back on that cleaning up data question, if there's any other kind of tips. The way that we kind of had things segmented is there was like 2 parts of our team. We had the more software-based side, and then we had the folks that would go in every day, use our software to actually look at it. So like Nick was looking every day at the dots on plots, as we called it, that we created. And so like if something went wrong, he would like stand up, yell across the room, hey, it's broken. and then we'd scramble to try to make sure everything was working again.
Yeah, so I lived kind of a 50-50 split between the analyst and the software developer, right? So I spent the first couple of years developing the software, and then I ended up doing a lot of the analysis on the other end of it, which is kind of a fun, 2-parter as far as curating the data and then actually looking at it and acting upon it. And I will say that if you are going to use some kind of machine learning model, right, to come up with answers that are actionable, one thing that I didn't really consider is that you better be prepared to explain it to somebody, right? Because if you tell somebody, hey, this engine needs to be pulled, right? You would think in a perfect world, they would say, oh, wow, this person must really know what they're talking about if they're telling me this. But the real answer is they're going to ask you immediately, why? You're telling me that I have to spend hundreds of thousands of dollars, potentially millions of dollars, Better have a good reason.
Yeah, and on that note, right, like that's why for certain cases you might want to use decision trees because you can actually open up the model. You can see exactly why you were going to pull that engine, whereas you use a neural network sometimes. They're working on it now where you can actually explain how a model got trained. I'm trying to remember the term, but I'm bad with words, so I can't remember off the top of my head. But they're coming up with ways of doing it. But for example, decision trees, and other models there where you can actually see why. I think even like linear regression, you can go in, you can see how much
You can see
certain
the weight.
variables impacted. Yeah.
Mhm.
Uh, those are good for when you have to explain to someone why they need to be pulling
Right.
something that costs millions of
Yeah. Like,
dollars.
for example, in this example today, right? We ended up filtering out, I think, 6 of the sensors, and we ended up using like 18 of them to create our model, right? And that gave us the best performance. But if I were implementing this in a real case and I had to defend it and I had to explain it to an engine manufacturer, right? I may not use all 18 sensors. I may boil it down to maybe 10. And even if it's a small hit in accuracy, if it makes it a lot better and a lot more concise to explain, that I can say, hey, listen, I'm using the temperature probe at station 4.1, right? Because that's your turbine inlet temperature, and that is the most important one, right? The people that design the engine are going to hear that and say, that makes sense, right? I'm going to tell them that I'm going to be using the fan flow rate as one of the parameters, right? Because that's a big indicator on your health of your turbine that's driving it. Those people they'll understand that. Whereas if I just say, yeah, I'm throwing all these 18 sensors into my machine learning model and it's telling me yes or no, right? The people that might want to implement that model might look at you and be like, well, we don't trust that because we don't know what your model is doing, right? Because they didn't design it. And we're not just going to blindly take your answer. So there's an
Yeah.
interesting, play there.
And so, like, a question just came in. I think it's going to be one of the last questions we kind of answer here before we move on to the raffle. But what is the future of ML? Like, Nick and I were not machine learning experts, so we can't speak to the future of like ML broadly. But within the context of what we did, uh, machine learning was interesting, but you couldn't use it to make major like life decisions, right? So you would use machine learning to kind of narrow down what the issues were, but you always had a human come in. So it's a great way of prioritizing and narrowing down a huge amount of data coming in. But in the end, at least for what we did, we always had a human to make the final decision and to explain it. So we always made a report on everything that we did.
Yeah, and I love that answer. I'm going to expand on it a little bit. So my world was mostly a military one, as far as jet engines go, and they fly them a ton, right? Like an absolute ton. There's no way that you're going to have a person look at the data from every flight, right? So what we had models to do is it would look at every flight and it would just assign potential issues and a weight as far as confidence goes, right? So every day that I would come in, I would have a summary of 10 or 15 flights that have set flags, and it'll say, this engine may be having turbine issues, right? This engine may have a nozzle issue. This engine may have, a fan issue at this and this confidence, right? And then I would look at the data itself, right? Actually, not even the raw data. I would look at a average data over a bunch of flights, right? And put my analysis to it and say, oh, no, look, this engine just flew in Alaska instead of flying in Hawaii, right? This is not a real alert. It's just the temperature changed 70 degrees from here to there, and that just made it look a little different, right? And that may feed back to the models itself. I might say, oh, well, this needs to be more related to temperature so that I don't get these false alarms. Whereas I may get an alert that I look at and go, oh, wow, that looks pretty bad, right? Now I'm going to take this data and I'm going to package it up and I'm going to send it to them and say, hey, listen, we set this flag. This data looks to me like it's real. This is what I think is happening, and this is why I can back it up. And then it's on them, right? So I think machine learning will, as it gets better, right, those predictions will get better. and the amount of time that an analyst has to spend determining if they're real or not may change to the analyst being able to be more specific about the ones that are real because they have less false alarms to look at.
Right. Yeah. But then again, we still had to explain the model. So we would train this huge, we would train the model on this huge data set. And then when, before we implemented it, we had to explain exactly how that model worked to somebody on the other side. So you always still have to explain it. So I think it's time to move on to the raffle. This is a big moment that I'm sure all of you have been waiting for. I know Justin really wants to see my React pages. So let's see if it works.
All right. This is a beautiful React page.
Yep. I'm a designer.
I just need a list of contestants. Give me 1 second.
So this page is actually being hosted in CML, so in public cloud, and it's in the applications in CML. So that's another feature that you have there. It's a nice way to interact with your data and your models. So basically, it's a Flask in the back end, and the Flask is hosting these React pages. I think we're going to try to do something around that, whether it's video or a meetup where I can show how I did this, and maybe I'll make like a nicer example that time, or we'll show this page again once I've designed it a little more.
All right. Everyone see the contestants?
I see them.
All right, you ready? And the first winner is Naresh. Ooh, that's a tough one.
You have to do it. I'll be worse.
Chun Chukala. That is my. I apologize, Naresh, but Naresh Chun Chukala is what I'm going with there.
All right, great. Oh, and I should mention, stick around to the end to the prize winner. You can either, if you have LinkedIn, connect with me directly, Mark Shoney. I'm sure my name is somewhere on there, and then we can coordinate to get you your prizes. Or you can email socialmedia@cloudera.com. There's no spaces, no dots, or sorry, no dashes. Of course, there's no spaces. It's an email address. So no dashes, no dots. It's just socialmedia@cloudera.com. So just make sure you get in contact with us because we can't get you your prize unless we know where you are. So.
All right. Congratulations, Naresh. Time for the next winner. Danuj Kolathu Parambil. I apologize. That's not the best at pronouncing names, but Danuj, congratulations. You are the second.
We'll be honest. Tui, who's there manning the video feeds, we couldn't even pronounce his last name until yesterday. So that's how bad it is.
If I'm consistent, it's that I'm consistently wrong in pronouncing things. So
I just want to make sure that George, did we get those 2 winners, or Bill? Someone give me a thumbs up before we move on. I just want to make sure that we have the names. Okay, hold on. We're still collecting those names.
Here, I got it. Okay, we're good. We're good. We got them.
You good? You got them? Okay, so Nick's got the names. Perfect. I need to add that as a feature. I need to put something so every time a winner gets selected, they get put to a different list. I can do that. Maybe that'll be in the next thing.
One more thing before we lose everybody too, Mark.
Yes. Oh, yes. Nick, you want to read it off? I think you can see your screen a little bit better.
Yeah, absolutely. So the next meetup that we're going to do is on December 1st, right? And it's going to be covering Apache Ozone, breaking the 10 billion object barrier. It's going to be at 9 a.m. Pacific time, and put the link there. If you had a good time here, like recommend that you go check out the next one too.
Great. Well, make sure you check out that meetup. Where make sure you answer the survey questions, right? We want your feedback. We want to know how we can do better and make this more exciting for everyone. Thank you so much for joining today. Hopefully you enjoyed our banter and the presentation. And if you did like it, we'll be back. If you didn't, we probably won't be back. Just kidding. They'll find some other presenters. So bye, everyone. Thanks for joining. See you next time.
Goodbye, everybody.